Welcome back to this video on decreasing and increasing functions in our level 2 calculus. Alright, so this question is a very common question in the exams and it's always available for a pretty high grade. Normally it's an excellence level question. So basically an increasing function is the part of the function where the gradient is greater than 0. So basically the gradient is higher than 0, so as x increases, y also increases. The decreasing function is the exact opposite of that. So basically it's when the gradient is less than 0 and when the graph is decreasing. So when y is decreasing as x increases. So as we go further along, the y is decreasing. So decreasing over time. And for these types of questions, your claims always need a justification. So basically that's just using a diagram to prove. And this is very typical questions, like I was saying. It's usually like 90% of the time it's available for excellence. So just an example here, we have a parabola. So to the right here, our graph is sloping upwards, so therefore it's increasing and x is greater than 0. So gradient is greater than 0. To the left side here, as you can see, the graph is sloping downwards and therefore it is decreasing. The x is less than 0. Good example, okay, so we're going to look into an example of a question. So the function f of x equals to 4x cubed plus 6x squared plus x plus 9 is drawn. Kevin wants to know the x values of the graph, x values of when the graph is decreasing. He also needs a justification as he is stubborn, okay? So first step here, okay, is to differentiate the function. And your answer should come out to be 12x squared plus 12x plus 1. Okay, so now we need to use our calculus methods here. So we know that when the graph is decreasing, the gradient is less than 0. And right now we have the gradient function. So therefore we can say when the gradient is less than 0, so therefore when the gradient function is less than 0. So we can make our gradient function is less than 0. So therefore 12x squared plus 12x plus 1 is less than 0. Okay, so now once again we're just solving the inequalities here. We're going to be making finding the x values, and then we're going to find the range of x values there, okay? So we're going to solve for our x values. So graphics calculator works best. So x equals to negative 0.092 or x equals to negative 0.908. Okay, so now we have to use some logics here, okay? So we know the justification and the range of values right here. So we know that this is a positive parabola. So this is a positive parabola because a is positive. And what is our a value? Our a value is the 12x squared. You know that is positive, so therefore the whole parabola must be a positive parabola. So therefore it is a happy parabola and is sloping up, okay? So just the graph should look something like this. So refer to the right. This is our happy parabola. Should look something like that, okay? You want to know when the gradient is less than 0. So identify the areas where the y is negative. So basically, in other words, identify when the graph is below the x-axis, okay? The graph is below the x-axis, okay, as you can see, it's between our x-intercepts. Between our x-intercepts, the graph is less than 0, so therefore our gradient is 0 at those parts. So therefore, we're going to write our concluding statements here. These values will occur between the x-intercepts. Hence, x is between negative 0.092 and x equals to negative 0.908. And just a little bit of a note, remember to indicate to the marker what part of the parabola your intended answer is. In this case, mark the area between the intercepts. So like I've done with the blue highlighter here, I want you to, well, not necessarily highlight, but I just want you to mark the place where it's where your intended answer is. So just like make some sort of reference so that marker knows that you know you understand that where it is. Another way to justify is using the cubic. In my opinion, I don't really recommend this over the parabola. I'd rather you use the parabola because it's a bit easier, but you can use this if you want. So another way to justify is using the cubic. So we need to draw a rough sketch of the cubic and indicate the parts of the cubic where your answer is needed. So if we have our using the last question as an example, So when x is less than negative 0.908, we bring up the graph. Bring up the graph on the left hand side. So should I just bring up this graph? So when x is less than negative 0.098, so when it's on the left hand side, refer to the very left hand side. As you can see, the graph is going upwards, okay, going upwards to the maximum. And you know when x is greater than negative 0.092, so that's the very right hand side of the graph. As you can see, it's also sloping up. But however, when something is sloping up, that's the gradient is positive. We're looking for when the gradient is negative. And as you can see, between these two values, we have a graph that is sloping downwards, and that's what we want. So therefore, we can make a reference to mark the graph between these two intercepts. Okay, in this case. So as you can see, I've marked the area between the two intercepts, and that will be your final justification. So we're looking at one more example here. So we have the function f of x equals to negative 2 over 3x cubed plus 8x squared plus 2x plus 6. Find when the graph is increasing. So once again, follow through with our steps, differentiate. So our f dash of x equals to negative 2x squared plus 16x plus 2. Alright, so once again, we're going to solve, not quite yet. We're going to find when the graph is increasing. So when the graph is increasing, the gradient is more than 0. So therefore, we're going to make our gradient more than 0. Our next step is to solve. And if we solve, that's just basically using your graphics calculator to find the x-intercepts. So you get these two values, 8.123 and negative 0.123. Okay, so this is a negative parabola. So how can you tell if it's a negative parabola? As you can see, it's negative 2x squared. Negative 2x squared indicates a negative a value. And if it's a negative a value, therefore, it is a negative parabola. And we should see here that we should be drawing out an approximately sad parabola so we can understand. So we have it doesn't have to be exact. So as you can see, I've drawn this on Desmos here. It's very accurate graph, but however in the exam you just do a rough sketch, okay? Does not have to be accurate at all. You don't even have basically just extremely rough sketch, like you know what I'm talking, just not exactly perfect, okay? If we draw out this parabola here, we can identify the areas where the y value is greater than 0. So we're going to find when is the gradient more than 0, and as you can see, once again, this is between the two intercepts. Should have got a graph here, so I've got highlighted the part when it's greater than 0, and that's between the two intercepts. So therefore, our final answer here is x is between 8.123 and negative 0.123, and that's your final answer with the justification. So I've added a little bit of a note somewhere. Okay, so remember to justify your answer, very important. So you need to mark mark your graph where it's increasing, depending on the question, mark where your range of values are. Alright, so our last part of this video, we're going to be drawing the gradient function given a function, okay? So let's say we're given a graph here. So let's say we're given this parabola here. And then you are asked to sketch the gradient function. In this case, there are basically two very important things the marker looks for here. It's the x-intercepts is correct and the shape is correct, okay? So basically, I've highlighted this graph left and right. So on the left-hand side, as you can see, the gradient is negative. It's coming down to the minimum. So therefore, it's a negative gradient. And as you can see in the purple region, it is increasing because it's going up away from the minimum. So it's increasing. What does this mean? This means that when x is before the turning point, in our gradient function, it should be below the x-axis. And then after the turning point, it should be above the x-axis because it's a positive gradient. So as you can see, I've said here, so green is the graph sloping downwards. This will be under the x-axis in our diagram. This is because the gradient is less than 0. Purple is the graph sloping up above the x-axis in our graph, so therefore the gradient should be greater than 0 in this case. And the black dot is our turning point, and when there's a turning point, the gradient equals to 0. And there's a gradient equals to 0, that means on our gradient function graph, that will be our x-intercept. So our graph should be looking like something like this. So like I've indicated with the green and the purple, so on the left-hand side, it is green. The reason that it is green and it is below the x-axis. It is below the x-axis because back into our normal equation, our normal graph with the parabola is decreasing. And if it's decreasing, it's lower than 0, so therefore I've drawn this to be under the x-axis. And it's the same logic for the purple. It's above the x-axis because it's positive gradient, okay? And our black dot is our turning point, and therefore that is the x-intercept. So it doesn't have to be very accurate, okay? It could be as inaccurate as you want, but however, you have to keep in mind the x-intercept and the shape, okay? Other than the x-intercept and the shape, you can be as inaccurate as you want. Well, like, don't be, like, ridiculous, but, like, just be, like, reasonable, okay? So you don't have to pay too much attention to it, but don't be over ridiculous, if you know what I'm trying to say. I have one more example here, but it's drawing a gradient function from a cubic graph. So if we have a cubic graph this time, so we have cubic. If we were to sketch the gradient function, so once again, the marker is looking for the exact same thing. So the shape and the x-intercepts here, okay? So as you can see in this diagram, there are 3 regions. In the purple region, bring up the thing. In the purple region, the gradient is going up to the maximum, so therefore it is sloping upwards, and the gradient is more than 0. On the red region, this is the exact same logic. The graph is going up and away, so therefore it is also sloping upwards. The gradient is more than 0. However, in the blue section, it is sloping downwards. And if the graph is sloping downwards, that means that the gradient is less than 0. And we can see the 2 black dots. These 2 black dots is our turning points. And at our turning points, the gradient equals to 0. So therefore, on our gradient function, that is our x-intercepts. So remember at the very start of the video, I mentioned that a cubic becomes a parabola. So in this case, we'll be sketching a rough model of a parabola as our gradient function. Alright, so our graph should be looking something like this. So once again, the purple and the red is above the x-axis. The reason it's above the x-axis is because the gradient is positive. However, for the blue section, it is below the x-axis, and that's because the gradient is negative at that point, okay? And once again, our 2 x-intercepts are at 0 and -4, which is our 2 turning points on the parabola. That's because the gradient equals to 0. And once again, you don't have to be very precise, okay? Once again, just keeping in mind the shape and the x-intercepts, you should be fine, okay? But just don't be, like I said before, don't be too ridiculous with it, and that should be fine. And that does bring us an end to the video on our differentiation topic. Okay, I will be trying to make out another video, maybe on kinematics or an integration before the exam. I'll try my best, but no promises. But in the meantime, happy studying for the mock exams, guys. Good luck. Thank you. Bye.